Alrighty, 2.5 day 1 is where we are at. As I mentioned in 2.4, it's time to get a little more serious about transformations, okay? Before we get started, thinking of like big picture things about transformations that are just good to kind of be thinking about. I chose an absolute value and a square root function to work with today for two reasons. One, good to start working a little bit with some less common functions, right? Again, we spend so much time with lines and quadratics that it's time to keep kind of broadening a horizon and studying other types. And two, particularly with absolute value, it's pretty easy to see their transformations, right? It's V-shape, it just kind of works well, right? For kind of seeing what effect these transformations have on graphs. They're a good graph to use. It may not be the most common function that would come up all the time when you're modeling data, but it's a good one. It's a good one to see the transformations. All right, so if you have this plus 2 or minus 3, this kind of thing going on, adding or subtracting, what you are talking about, and you could label this whole slide. These are vertical shifts, okay? Because previously I had said with transformations, right? Now, but you're probably seeing the term in here. Well, you may come across it at some point called translations, right? I'm sticking with the book's vocabulary. You don't need to worry about the difference, okay? When I say transformation, we're talking about stretching or moving a graph, okay? But in the previous discussion we'd had, we'd said there's 3 types: a shift, a stretch, and a reflection. Today we're going to look at shifts and reflections. No stretches today, right? That's day 2, right? We'll talk about that more as we go on. Right here, if you're at the end, what that plus 2 does to your graph is it's shifted up 2. Okay, so if I were to create a graph of g of x, I'm just going to each point on the black graph, which is f, right? Not a bad idea to label them. The original graph, f, right, that's the absolute value. The function g is once that graph has been shifted up 2 units, which I'm doing in blue. And there is g. Okay? Vertical shift up 2 units. That's what that plus 2 does at the end. And if you see addition or subtraction, right, to the entire function, usually it's just sitting at the end of the equation, you've got a vertical shift. Here's h. It's shifted down 3. Shifted down 3 from f. There's h, okay? Good transformation to start with. You'll probably find once we've had the complete discussion that the vertical shifts are probably the most basic, right? They're the easiest to identify. They're the easiest to apply to a graph. But if you have that addition or subtraction at the end of the equation, it doesn't have to be at the end. We'll talk more later on about how to identify what shift is what when you have multiple, which isn't going to be a huge thing today. I think I have one example where you have multiple transformations. But the vertical shift isn't too bad to identify, but it only does one thing, right? If I put like a plus 2 or a minus 3 at the end of my function, all it has the power to do is take the exact same graph and it can move it up and it can move it down. That's all it does, okay? Can't reflect it, can't stretch it, can't move it side to side. You can just shift up and down. All right, same function, okay? Same function. Now, I'm here. I'm going to have to offer a little more evidence because I don't think you're going to buy it right away, so I'm going to have to make some tables. If you want to label this, looking for some space here, this slide is all about a horizontal shift. Okay, still sticking with the absolute value graph, okay? F is still just the absolute value of x, okay? So if it is in parentheses and the addition is specifically kind of paired with the x variable, okay, notice how the +2 is in the parentheses of f of x, not just at the end like it was in the slide before. That effect is that the graph is going to shift from side to side, not up and down. Okay, we call it a horizontal shift. Now here's the thing, I think I'll have some work to do to convince you. Right, it's going to get shifted 2 units. It's going to get shifted 2 units left. And then over here, you see the x minus 3. And that's going to get shifted 3 units to the right. Okay? Now, some of you might be like, okay, I buy it. It's a little weird that you see the +2 and you would think that's 2 units right? Because you, on a number line, you would equate like going to a bigger number or addition, right? Going to the right, and if you're subtracting a number or moving to a smaller one, that you would go to the left. I'll do the best I can here just by making a table. I'll give you a lot of the details on the first table, not so much on the second one. You're going to see, I'll give you the values, but you would see the same thing. What I would give you here is I would go -4, -3, -2, -1, and 0. Okay? I'll give you that hint for P of x. Those are the x values that I would use. Okay? And now what we're going to have here would be -4. Right? That's P of x, right? Immediately add the 2 to the x value. Well, it's inside the absolute value, whereas with the vertical shift, it was on the outside. But now it's on the inside. All right, we end up taking the absolute value of -2. And there we go. That'll be 1. Again, the second table that I make for R, I will not give you this much detail because it would be the same thing. And then we'd have, let's see here, 0 plus 2, right? I'm taking all the x values that I put in my table. I'm just plugging them in, and I'm evaluating them, and I have 5 points, right? Because this is just kind of like with this whole, okay, this really shifts 2 units to the left. This is kind of just a no-nonsense approach to take. Plot some points. See what happens, okay? -4, 2, so I go 4 over, 2 up. -3, 1. -2, 0. -1, 1. Oops. You're probably just hollering at me. Dude, last one. Not right. None of it's right. It's got serious issues. And it does. Okay, not serious issues. In the sense that, okay, they're fixable, you know. Everywhere there, I was pretty much, wrote a 2, I wrote a 0. Just a classic mix-up. Not really, but we'll pretend it is. All right, we found it. Okay, now you can definitely see the pattern, and I could have added more points to my table, but I didn't because, I didn't want to. But you can see the V shape, right? And again, that's why I like working with absolute values. The V shape is kind of easy to see what's going on. Again, the black one is F. This blue one that we just made, we'll call this, that's called P. And there we plot our table, and yeah, sure enough, that +2, it moved it 2 units to the left. Okay, it's kind of a quirky thing and can be a little bit tricky to keep track of. Okay, you may have some work to do with that can be kind of hard. It specifically that it not just does the opposite of what you would think it would do. It does you have the vertical shift, which we just saw, and that does exactly what you think it would do. Is that if it's on the outside of the function, the addition or subtraction, if you add, it moved it up. If we subtracted, it moved it down. And then all of a sudden, if it's horizontal, it has the opposite effect. Okay, it can be a little bit tricky. Okay, and I'll give you some points. I'm not going to give you all the work on this particular table. I'd give you these. If you wanted to pause a moment and continue investigating this, you could use those 5x values, okay? Get the y values and go ahead and plot it, okay? If you want to check that on your own, pause it now. If not, let's keep going. At the very least, if you wanted to check those, that would basically be the same work down here where I put in the 5 points. Again, I'm not going to do that for this one. 1 2 2 1 3 0 4 1 5 2. And again, if you're still curious about how this has the opposite effect, double check those points, right? I'm pretty certain those 5 points are legit. But if you were, curious to check, remember R of x, right? It is the absolute value of x minus 3, right? We gave it the transformation of subtracting 3. My graph of R didn't work out so good. Trying to clean it up a little bit. Got a little squiggly. That's all right. There's R. You can see on the graph, sure enough, like we've been saying, it moves 3 units to the right, right? 3 to the right. There you go. All right, we're switching up a little bit, going to the square root. Okay, I'm going to double up the last one because I'm going to do 3 of them. Okay, I'm going to do 3 of them. But I'm going to work in reflections. The 2 that we just saw on the previous slide would be described as shifts. Now we're going to do reflections. These 2, okay? I'm going to jump down to here. These are called rigid transformations. Now you might be looking at that thinking, what on earth? Okay, the 2 that we're talking about here, number 1, the 2 that we've seen, right? Shifts. And number 2 that we'll see here is a reflection. Specifically some reflection over an axis. Okay? The basic shape of the graph is unchanged. Okay? Think back to the absolute value examples that we saw. The thing with those, think of the V shape. This is why I like the absolute value with transformations. Think of the V shape, okay? There are ways, which you will not see today, where if you wanted to make the V a lot wider, like almost like it got squashed so that the lines are increasing more slowly, and it's a really, really broad, wide V. You can do that. If you wanted to make it really skinny, okay? If you wanted to make it really skinny, you could do that too. With the square root function, if you wanted to mess around with this and have it increase faster and look something like that, it can be done, right? It can be done. That involves changing the shape, and that category of transformation is called a stretch. That's tomorrow in 2.5 day 2 that we'll stretch them. Shifting and reflecting. We're taking the same basic graph, right? Again, if you look back in those examples with the absolute value, they're great. Because you can see with all the graphs that we made, the basic shape didn't change. All we did is we took the exact same V shape and we moved it up and down and side to side, okay? Reflections are the same way. We're not changing the shape. All right, negative sign out here, right? I'm gonna say it once again, let's make a table. Here's g of x. Again, I'll give you a little head start here on some good x values to use, okay? All right, so I plug that number in for x, and then I apply the negative sign. Won't do anything to the 0. -1 and -2. I'm just going to use those three. I think I can tell what I'm looking for from those 3 points. So I'd have 0, 0 right here. 1, -1, right? This graph is a tiny bit off. It should go through the point 1, 1 because the square root of 1 is 1. But it doesn't. It's a little bit too high, but whatever. It's approximately the square root graph. 1, -1, and there's 4, -2. And again, that was the graph of G, okay? Now you already know that negative sign, which we haven't seen before, that's a reflection, okay? So it's kind of like you got a couple things you got to keep track of. Remember with shifts, where you did the addition and the subtraction was important. If it was outside the function and kind of just at the end of the equation, it was vertical. If the plus or minus, so think in terms of the example we did, if it was outside the absolute value. In this case, it would have been if it's outside the square root, you would have had a vertical. If the addition or subtraction was in the inside of the square root or the absolute value, that would make it horizontal. Same thing with reflection. If that negative sign is on the outside of the operation, it's a reflection over the x-axis, okay? As you would think, if you put it inside, it's still a reflection. It's going to be a reflection over the y-axis, right? Same shape, same graph, right? Just reflected. Now, if you're kind of keeping track of transformations, you're like, okay, we had vertical shift, horizontal shift, reflection over the x-axis, reflection over the y. The end of the notes tomorrow will conclude with a table. That'll be a super important study guide for transformations where we'll put them all together and have basically like notation within a function to be like, oh, if you see this, this is what's going on. If you see a negative sign that's within the operation, oh, that's a reflection over the y-axis. So we'll kind of compile everything together. Here is our first look at 2 of them, okay? This is kind of the direction we're going to head. First of all, I see shifted 2 units. Which direction? left. And I also see reflected over the x-axis. So another thing that's going to come your way a little bit in day 2 is multiple, right? Multiple transformations. Okay, here's 2. A lot of times when you're working with an equation, we saw this all the time with quadratics. You had no idea what was going on because we hadn't studied transformations. Some of those had 3, right? And it's realistically possible that, well, 3 or 4, right? Most equations that you work with in word problems probably have 3 or 4 transformations so that it fits the data appropriately, okay? I don't know on a test if I'd throw 4 transformations at you. I might. I would definitely be able to, I'd expect you could handle 3, right? So at the end of the first day, here's 2, okay? And you if you're looking at how they relate to a graph, one at a time, right? I've already seen, right? So first of all, the graph in blue, that was reflected over the y-axis. This problem has nothing to do with that, right? Nothing to do with it. I could go back to graph G that's in red. I could work with that. Because that one kind of applies because it's been reflected over the x-axis. Mine needs to do that too. The only thing I also need to add to it, okay, again, I'm specifically talking about the graph in red. I would need to take the graph in red and I need to shift it 2 units to the left, okay? And remember, the key points I put on it were here, here, and here. Those are the 3 points that I have in the table, okay? So that needs to go to here. That needs to go to there. And that needs to go there. Same shape, same graph, shifted 2 units to the left. Okay, now we kind of had a head start on that one because the first transformation I had already done in G. Okay, but it still gets to the main issue that if you have multiple transformations going on like that, take them one at a time. That's the whole key, right? So I'm writing down here and identifying them because you'll be asked to do that too. Because you want to do that. When you look at an equation that's got multiple, or a function that's got multiple transformations, you want to be able to identify them because each transformation does one thing, right? In this case, the negative sign out front reflects it over the x-axis. The +2 shifts it 2 units to the left, okay? Because then in terms of like applying them, you would go through one at a time. And again, typically you would expect in the next couple of days, I might ask you to do 3. In your homework, you'll come across 4. The question would be on a checkpoint or a test, would I ask you to do 4? I could. I would certainly throw that out there. I'd feel fine doing it. That's a hard question. I feel more compelled to look at 3 because that's the case I really, really want you to be able to do is identify and apply 3 of them. All right, having said all that, that gives us a pretty clear direction of exactly where we're going in day 2.